Hello, and welcome to my final year project video. Today's topic is developing AI attacks or defenses, and the area of focus will be asynchronous multi-agent reinforcement learning. In the new age of the internet, technologies using artificial intelligence such as self-driving vehicles, automated translation and image recognition have been globally adopted and utilized around the world. Machine learning is a subfield of artificial intelligence and are utilized in many applications. One of the machine learning methods is reinforcement learning. Our area of focus is asynchronous multi-agent reinforcement learning. But before going into asynchronous multi-agent reinforcement learning, we need to understand how multi-agent reinforcement learning works. For multi-agent reinforcement learning, there are three agents: Agent 1, Agent 2 and Agent 3. All three agents have the same environment that they are in. Agent 1 will exert an action called Action 1, likewise for Agent 2 and Agent 3, as they will exert an action called Action 2 and Action 3 respectively. All this changes to the environment will be like a concatenation of all three actions: Action 1, Action 2, Action 3. Then the environment will transit from original state of 0 to environment state of 1. Next, the environment will return the same state of 1 to all three agents. There is also reward as well. This reward is self-constructed. The person who creates the agent decides what this reward is. This reward is to reward the agent for taking good action on the environment, and bad action will result in poorer reward. So, for the agents to improve, in each round, the agents will collect information like the previous state, current state's action, the next state and the reward for this particular round. This will be put into a database. From this information, it will tell where the agent was, what action it took, where it ends up and what is the reward given. Through this, as the agent collect more and more information, it will take a few samples and then train the agent using this information. This is called the trajectory. So, trajectory will be used to train the agents where it updates parameters. After it updates the parameter, it will continue the action, obtaining of state and reward and execute action, and then eventually somewhere down it will have enough data to train again. Then the parameters of the agent will update again. Theta is the parameters. The parameter is neural network weights. This is how reinforcement learning works in a multi-agent scenario. So after explaining what is multi-agent reinforcement learning, we know that all agents receive the same reward. It means that they are all cooperating to serve one single task. However, all agents will produce their own action simultaneously, not knowing what the other agents are going to act. Hence, they have no idea what the other agents are acting. This shows that independent multi-agent reinforcement learning do not respond well to asynchronous actions. Multi-agent reinforcement learning methods to date do not work too well handling asynchronous methods. Hence, further research can be done on multi-agent reinforcement learning for asynchronous actions. For explanation of asynchronous multi-agent reinforcement learning using the example in this slide. There is Agent 1. Agent 1 will take an action called Action 1 to the environment. Then the environment will undergo some changes and pass the state to Agent 2. At Agent 2, it will receive this state and execute an action called Action 2 on the environment. Now the environment will be a new environment after Action 2. After this change in environment, it will present Agent 1 with a new state. This is called asynchronous multi-agent reinforcement learning. Since it's asynchronous multi-agent reinforcement learning, Agent 2 will be affected by the actions of Agent 1, and the actions of Agent 2 will affect the environment, so that Agent 1's subsequent action will be influenced by Agent 2's previous action. If I were to use traditional multi-agent reinforcement learning asynchronously, there will be sparsity in action and state space. Hence, I will be focusing on asynchronous multi-agent reinforcement learning for the problem. We proposed a simulated environment which users will be walking around their neighborhood with their user devices, UDs for short. In the neighborhood, there are multiple base stations that interact with the UDs in the neighborhood. The user devices can download from the base stations or upload information data to the base stations. The users in our simulated environment are constantly moving. The main goal of our work is to minimize the total time UDs take to download and information data from the base station's wireless communications, and to control and manage the power output for uploading information data to the base station. There are three base stations that have channels allocated to three user devices, UDs. In each turn, each of the three UDs may or may not be allocated a base station, and there can also be more than one UD allocated to one base station. This allocation is done by Reinforcement Learning Agent A, for any download of information data from base stations to UDs. On the other hand, during the data upload phase from UD to base station, where user makes some changes on their end and upload the information data back to base station, Reinforcement Learning Agent B will decide the power allocation for the upload transmission. The goal for Reinforcement Learning Agent A is to minimizing data download time to users through optimizing the user base station allocation. The concern for Agent B is that the UDs cannot expense maximum power all the time, as this will result in great interference. So, the goal for Reinforcement Learning Agent B is to control and manage the power output to reduce transmission delay. Since downlink, downlink, uplink are executed asynchronously, so we adopt our asynchronous reinforcement learning architecture. For our experiment, we configured a network setting, 3 UDs and 3 base stations to test our proposed approaches and algorithms. At the beginning of each train step, each UD and each base station are placed uniformly at random in the simulation environment, which is a 1000 meters times 1000 meters area. At the end of each time step, UDs randomly move a maximum of 100 meters in X and Y directions, in which X and Y represent the longitudinal and latitudinal directions. Next, we implement the 4 commonly known reinforcement learning algorithms, which are Deep Q Network Algorithm, Dueling Deep Q Network Algorithm, Advantage Actor-Critic Algorithm, and Proximal Policy Optimization Algorithm. To better observe the final performance, we train the models with 300,000 train steps for network setting, 3 UDs and 3 base stations. For result analysis, the 4 algorithms mentioned previously are tested under 3 different scenarios, to compare the results. For key findings, Advantage Actor-Critic performs the best among them across the 3 different scenarios. It always attains the highest eventual reward, which can be attributed to its Advantage Actor-Critic base structure and superior sample efficiency, as it uses multiple agents for sampling and gives one of the shortest delay for transmission of uplink and downlink of data. Next, Proximal Policy Optimization Algorithm comes in as a runner-up. Although PPO is considered a more stable algorithm due to its policy constraint feature, it fails to find a near-optimal solution in our proposed scenario under transmission rate, for uploading information data right at the end. Next, Deep Q Network Algorithm performs the worst of the algorithms due to its inability to handle complex environments when the state and action space are enormous, and it also gives the worst delay for transmission of uplink and downlink of data. Lastly, Dueling Deep Q Network Algorithm performs around the same as compared to Deep Q Network Algorithm under the transmission rate for uploading information data scenario, and it obtains shorter delay time than Deep Q Network Algorithm, for transmission of uplink and downlink of data. In conclusion, asynchronous multi-agent reinforcement learning improve how the agents act in an asynchronous environment, with an example which aims to model mobile users' devices traveling on the go, and downloading and uploading information from the base station in real time, using 2 reinforcement learning agents. The experiments demonstrate that Advantage Actor-Critic algorithm performs best in our proposed scenario. Next, our study can be viewed as a use case of asynchronous user devices and base station interaction. Lastly, a future direction is to investigate other ways to improve the performance of reinforcement learning in an asynchronous environment. And that concludes the video. Thank you for your attention.